Welcome to part 4 of this series. In this video, we'll try to understand the complexity of relations between multivariable differentiability and partial derivatives. So in previous part, we proved that the existence of continuous partial derivatives in the neighborhood around point of interest implies differentiability of a function, which means that a function can be locally approximated with the best linear approximation. And differentiability implies continuity, which can be derived from that proof. And secondly, I gave you an easy exercise to show that if conditions for differentiability hold, then partial derivatives necessarily exist, and they form constant coefficients in our linear expansion. And again, differentiability implies continuity. So for counterexamples, let's look at this function. I want to prove that at a point 0, 0, it is continuous. It has partial derivatives at that point, but it is not differentiable. So that means that in this first theorem, continuity of partial derivatives in the neighborhood is a necessary condition. So continuity is quite easy, but to be more rigorous, we can use polar coordinates, and using delta epsilon definition of continuity, if this radius is less than delta, so this the distance of a point xy from 0 is just r, then the function value at xy minus this is simply that, right? Because at 0, 0 function is 0. Using polar coordinates, we rewrite it like that. And we can take r outside because we know it's positive, it's a radius. So now if we assume that, well, we can see that this is less than delta root cos theta sine theta. And of course, this product is bounded above by 1. So this is overall less than or equal to delta. So we can just take delta to be epsilon in our continuity definition. Now let's do partial derivatives. If you try to apply implicit differentiation, then you will see that at 0, 0 you can't calculate it. So we have to use the limit definition of a partial derivative, and we basically get x naught plus delta x y naught, our function value for partial derivative at x, minus root x naught y naught over delta x. But of course, x naught and y naught are 0, right? We're interested in point 0, 0. So this simplifies down to basically, sorry, of course, this is not a comma here. It's a bracket. So this is simply 0 divided by delta x, because both of these square roots are 0 when x naught and y naught are 0. So this is 0, and this is our limit as delta x tends to 0. And this is f at f with respect to x. Likewise, we can get that partial derivative with respect to y is 0. But it is not differentiable. Why? Well, assume it has a linear approximation like the one we stated in the previous video. So suppose that we can calculate this value with a times delta x plus b times delta y plus some functions that depend on delta x and delta y and which decay faster than delta x and delta y. So this refers to part 3. So make sure you understand why I write this expression down when I want to consider differentiability. So the question is it possible? So suppose I take, so if this holds in the neighborhood around 0, 0, this should be true for any delta x and delta y. So suppose I take delta x equal to delta y. So I give same length of an increment in each direction for my function. So this now turns to simply delta x as a plus b delta x plus o little of delta x. Remember, when I add two o little functions of the same variable, it just becomes one function of delta x. So then if I rewrite this expression, I would get that a1 minus a minus b delta x is supposed to be o little of delta x. But by definition of o little, I should have this guy going to 0 as delta x tends to 0, right? So does it happen? Well, clearly, if I divide both parts by delta x, I get this. And this is a constant. So this does not tend to 0 as delta x tends to 0. So this approximation cannot be true. And therefore, f is not diffable at 0, 0. So if you want to know why, you can try and find a general expression for your partial derivative and see that this function is not going to be continuous. So the first theorem is not, the conditions of the first theorem are not satisfied. Now let's look at the second example. We have a function. Clearly we can't divide by 0. So this definition only works for these x and y's, but we add 0 at 0, 0 artificially. Well, for this function, you can show that it's continuous on the neighborhood around this problematic point. We have bounded partial derivatives, but again, this function is not going to be differentiable. So again, we have x squared, y squared. This reminds us of polar coordinates, so we use them again. And then we get that f is r squared cos theta sine theta divided by r squared root r squared. And this is equal to r cos theta sine theta. So again, if r is bounded below by delta, then f is going to be bounded below by delta So we can take epsilon equal to delta. So I'm doing a lot of shortcuts here. If you are not following, then write it down and do it yourself. For partial derivatives, let us find expressions for, say, fx. We have that it's y over x squared plus y squared. And then when we use quotient rule, or here I'm using product rule, we do minus x squared. So first is going to be xy over 2 times 2x, and then we'll have x squared plus y squared to 3/2, right? So just double check in case I made any mistakes. Now, if I collect them all in one fraction, I would get that. On the bottom, this is going to be y cubed. This is going to be y x squared plus y squared minus x squared y after all simplifications. Now x squared y here, x squared y here cancel out, and I get y cubed over this fraction. Again, if I use polar coordinates, I get r cubed cos theta sine theta. Here I'll get r squared to power 3/2 is going to be r cubed, so they cancel out. And so I get cos theta sine theta. So now if I take absolute value of everything, I get this, 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 and so on. And this is, of course, bounded by 1. So actually this holds for all x and y that are around 0, 0. So do the same for fy to show that it's bounded. So using our definition of a function, suppose I can write, if I give delta x, delta y increments to my function, suppose I can write that delta x, delta y over delta x squared plus delta y squared, which is my new function value in the neighborhood of 0, 0, can be expressed as delta x, a delta x plus b delta y for constants. So once again, look at part 3 if you're unsure why I'm doing this. And we should have functions o delta x plus o delta y, which, by the way, can be replaced by o little that depends on the distance. So it depends on delta x squared plus delta y squared. Now here we can do the same trick. So this linear approximation must hold for any increments delta x, delta y in my neighborhood. So if I take equal increments, I get delta x squared divided by delta x root 2 should be equal to a plus b delta x plus a function of delta x. And again, so delta x cancels, this becomes 1. If I bring everything to the left-hand side, I get 1 over root 2 minus a minus b should be equal to o little of delta x. And this is again not true, because as I divide by delta x, this becomes a constant. And it clearly does not tend to 0. So this function is not differentiable even though partial derivatives were bounded. So once again, and you see it was continuous. So differentiability does imply continuity, but continuity can take place without differentiability, right? So once again, this theorem proves to be maximal. This theorem can't be extended. So here's my function, and you can see how at the origin we cannot really put any plane. Any plane will be a bad local approximation, because in some sense points go up and down, and this plane is not going to be a good representative of function at the origin. Let's have a third final example, which is actually very informative. So I feel like it's a monster example. We have the following function, two variables. It's x squared plus y squared sine x squared plus y squared at all points x and y such that they are not simultaneously zero, and we add artificially, so we call it its function is equal to 0 at this this problematic point. So as it turns out, what we can show is that both partial derivatives exist on any neighborhood around 0, 0. They are unbounded, but discontinuous at this point. Nevertheless, f of xy is differentiable at 0, 0. So again, this does not contradict our theorem, because in this theorem, implication goes only one way. So if we know differentiability, we do know that partial derivatives exist, but they are not necessarily continuous, which is what I put in my second theorem. So this example will prove that we are right. So if we are not differentiating at our problematic point, we can find out partial derivatives with respect to x and y just by doing differentiation, treating y as a constant in here. So you can do it yourself, and I'll just tell you the answer. I got that it's 2x sine x squared plus y squared minus this and there is a similar expression for partial derivative with respect to y. So notice how if I do not allow both x and y to be 0, this expression is well defined. So this proves us that fx and fy exist on any neighborhood around this point 0, 0, but we need to exclude that point. So this is our point 0, 0, but this expression is not applicable to this point. So we know that these partial derivatives are defined on a neighborhood excluding a point. But what about the point itself? Well, since this expression is not working, we need to use the limit definition. So we have to take the limit as delta x tends to 0 of f delta x comma 0 minus f of 0, 0 divided by delta x right? Because we are interested in this point specifically. If I plug it in, I get delta x squared sine 1 over delta x squared divided by delta x. I can cancel out delta x's, and I'll be left with the following. And of course, sine function is always bounded above by 1, so I can just do modulus, and this is going to be less than or equal to delta x, but it's going to 0. So my limit exists, and it is equal to 0. Likewise for fy. So this specific limit shows us that partial derivative at 0, 0 is simply 0. So now we can include this point into our neighborhood. What about them being unbounded? Well, if you look carefully at this expression, suppose I go along a line y equals 0. So if y equals 0, then my partial derivative simplifies down to 2x sine 1 over x squared minus 2x over x squared cos 1 over x squared. So now I see that I can cancel out x here and here, and I'll be left with minus 2 over x as a factor in front of cos in my expression. But I know that as x goes to 0, this guy goes to minus infinity. Now this guy, sine of 1 over x squared, is bounded, and 2x simply decays when x goes to 0. It also decays to 0. So actually, if I am purely on x-axis, so my y-axis, my y is 0, and I approach the origin, I get that my partial derivative grows in the negative direction in an unbounded way. So do the same for this partial derivative and see what happens to that. So they are unbounded, but this does not contradict our function being differentiable. So why is that true? Well, using the limit definition, I figured out that fx is 0, fy is also going to be 0. So I have a guess that for points in the neighborhood of 0, 0, I can write 0 times delta x plus 0 times delta y plus some little o of both increments. So actually, it is just the same as claiming the following. So actually, my function is just O little of delta x plus O little of delta y. So is this true? Well, let's plug in delta x and delta y to our expression. Sine 1 over delta x squared plus delta y squared. And we're going to use the same trick. So if delta x equals delta y, this becomes 2 delta x squared sine 1 over 2 delta x squared. But now, if we want to confirm that it's O little of delta x, we need to divide it by delta x. And what do we get? We get that it's 2 delta x sine 1 over delta x squared. And of course, this goes to 0 as delta x tends to 0 because sine is bounded. We can similarly do it for delta y. So if we just plug in delta y into this expression instead of delta x, this is also going to work. But actually, to be more rigorous, we can just rewrite this guy like that. Right, I just split the bracket. Sine 1 over delta x squared plus y squared. And it's very easy to see that this gives me a function O little of delta x, and this gives me a function of O delta y. So our guess was correct, and it is differentiable. Quite surprising. So if I plot my function, I can see that globally it decays because partial derivatives decay to minus infinity, so it makes sense. But as I try to look closer to my origin, here, for example, I see that I have arrived at some sort of kink, some sort of discontinuity. And if I zoom in closer, I can see how this surface is irregular. So remember that sine of 1 over x squared jumps a lot as it approaches 0. So you can sort of gain intuition on why this function had very strange partial derivatives. Nevertheless, as you zoom in closer, it becomes flatter and flatter, becomes really flat. So at the origin, in some neighborhood, we can approximate it with a plane. A little postscriptum. In these 4 videos, I used functions of this kind heavily to define and prove various things, but it may not be the same approach as you're used to from textbooks or lectures. This is the case because with calculus, there is what's called a standard and non-standard approach. So what I did is primarily known as non-standard calculus, which is all about infinitesimal functions. Functions that decay to 0 at a certain limit, like these functions do. Whilst standard calculus generally is described as delta epsilon calculus. So for example, in R2, in standard calculus, you would call a function differentiable if the following limit is equal to 0. Right? So here actually I have assumed that my function maps from R2 to R2. So this is my new value, this is my old value, and this t is a linear map. So it is some sort of matrix. And the function is differentiable if this limit tends to 0. It looks like it has nothing to do with the way I defined differentiability in R2, but actually it is the same as approach we did in part 3. So these two approaches yield the same result, but I find the non-standard approach a bit more visual, and it allows you to actually feel what's going on with derivatives and differentials. And at some point in the future, I will dedicate a separate video to the difference between the two, but you can conduct your own work or research to find out how notions from one translate to notions in another.